In this talk, I describe a thread-based concurrency model for JavaScript with cooperative cancellation. We first motivate the need of a thread-based concurrency model. JavaScript programs often have concurrency errors due to data races. Existing constructs, like promises, do not prevent event race. We propose a thread model where a thread is essentially a function that takes a thread ID as input and returns a promise value. Through the thread ID, a thread can be canceled, paused, and resumed. The shared states between threads can be protected by synchronization primitives such as envars and channels. We also discuss application scenarios of our thread model, such as data streaming applications, and the runtime overhead of our design. We first motivate why it is useful to have a thread-based concurrency model for JavaScript. JavaScript concurrency is based on its event loop, which consists of a call stack, a set of web APIs, and a callback queue. Asynchronous code on the call stack may invoke web APIs, which register callback handlers to wait for some asynchronous events. When these events occur, the callback handlers are placed on the call stack to run, which may register even more callbacks. The event loop checks events on the callback queue and invokes the registered callbacks when the event occurs. Concurrency error may occur due to unexpected occurrences of events. For example, suppose we register button handler to make remote request each time the button is clicked. This handler is registered using the code shown on this slide, where we set a callback handler for the click event on a button object. So when the button is clicked, an AJAX request is made. The handler to the button click event is persistent, which means every time the button is clicked, an AJAX request will be made. After the button is clicked, an AJAX request is sent. A callback is registered to wait for the AJAX event. However, the remote server may not be equipped to handle multiple concurrent requests, which can lead to a server error. Normally, if the AJAX request completes quickly, there will not be any problem. That is, if the button is clicked, that is, before the button is clicked, the previous request has completed. This way, there will not be any concurrent requests. However, if remote server is slow, then multiple requests may be generated from the button clicks, which causes the server error. This type of errors can be difficult to debug since it is due to the incorrect state of the server instead of the client. Promise abstraction help convert callback chains to sequential statements, but it does not help us in this scenario. Event race is still possible since promises do not provide synchronization primitives to protect shared resources. In our example, there is a race between the button click event and the AJAX event, which cannot be resolved by the promise abstraction. We can protect shared resources using a hypothetical locking mechanism so that before accessing the remote server, the callback handler gets a lock first, and then it releases the lock when the remote request completes. When the button handler runs, the first thing it does is to request a lock. After obtaining the lock, a remote request is sent, and the callback handler to the AJAX event is responsible for releasing the lock. After the AJAX event is received, the lock is released so that the next button click can grab the lock. If the button is clicked before the lock is released, then the get lock computation should be blocked. We can imagine that the blocked get lock computation can be made a callback to some type of block event. When the previous AJAX request completes, the lock is released. After the lock is released, the callback waiting for the lock event can run. But what if we want to cancel all the pending requests? A concurrency model with threads can make it easy to define locks that can protect shared resources. Blocked threads can be canceled through thread IDs so that application programs do not have to explicitly manage the life cycle of the asynchronous computation. In this case, there are two possible callbacks. One is for the AJAX event, and one is for the lock. Our concurrency model is based on a thread abstraction, which is defined as an object that wraps a run function that takes the thread ID as input and returns a promised value. Our thread has a monadic interface that uses the function pure, fmap, and a bind operation to compose thread computations. The lift function converts an asynchronous call to async object so that asynchronous call can be canceled. Using this thread design, we can implement the previous example using a lock. We define a lock with an envar object, which may be empty or hold one value. A thread can take a value from a field envar or put the value in an empty envar. A thread that put the value in envar will be blocked if the envar is full, while a thread that takes a value from envar will be blocked if the envar is empty. We also create a thread ID using an instance of a progress class. The button handler first gets a lock by putting a number in the envar m. Then it sends the AJAX request. When the AJAX request completes, it releases a lock by emptying the envar and run the callback with the result of the AJAX request. The button handler is a thread that must be started explicitly by calling its run function with the thread ID p. Here we illustrate a scenario where the button is clicked twice. The second click happens before the first AJAX request completes. The two clicks will start two threads. Thread 1 is due to the first click, which will grab a lock by putting a number in the envar m. After the envar is filled, is showed in red color. Thread 1 will then launch the AJAX request. Thread 1 will wait for the AJAX request to complete when the button is clicked again. So when thread 2, which is due to the second button click, is trying to grab the lock by putting a value inside the envar, it is blocked because it's already full. After the AJAX request of thread 1 completes, thread 1 releases a lock by emptying the envar. Thread 1 then runs its callback. Then thread 2 can proceed to obtain the lock by putting a value inside the envar. Lastly, thread 2 can start its own AJAX request. So how can a thread be canceled? Since JavaScript is non-preemptive, a thread can only be canceled when it is blocked for events. Here we illustrate when a thread is cancelable through a thread ID or a progress object. When thread 1 makes the AJAX call, a canceller is registered with the progress object P. So when the thread is waiting for the AJAX request to complete, user can cancel thread 1 by canceling P. Similarly, when thread 2 is blocked waiting for the envar M to become empty, it can also be cancelled through P. In fact, if we cancel P, both threads are cancelled. When thread 1 completes, thread 2 may also be cancelled when it is pending for an AJAX request to complete. We can also cancel a thread from a different thread. For example, the thread M in this slide makes an AJAX request, performs some computation, and displays the results using some DOM events. The variable T is the thread ID of M. We can start the timeout thread that waits a second before calling cancel on the thread ID of M. Like the M thread, the timeout thread is started explicitly. The thread M may be cancelled when it is pending for its AJAX request to complete, or while it is blocked for some DOM events. We have evaluated the usability of our design using a data streaming application that visualizes voltage and current signals into real-time charts. This application uses 4 threads and 3 channels, which are bounded buffers implemented with envars. Thread A fetches electric signals in batches from a remote data server in regular time interval and sends requests to a request channel. Thread B fetches the request, waits for it to complete, and distributes the result to a voltage channel and a current channel, so that thread V and thread C can read data from these channels and display them in separate charts. The voltage chart and the current chart can be parsed separately, which is implemented by parsing the thread V or thread C. All threads can be cancelled altogether, since these threads are forked from the same parent thread. So here's our example application. So this is the streaming of the voltage and the current data. This is supposedly in real time. Obviously, you can make it run a little bit slower, like this. Increase the in-time interval. So we have these controls allow us to pause and resume different charts. For instance, here I can pause the voltage chart, and notice that the current chart keep running. So they're implemented by different threads. So if I pause the voltage chart, I simply just pause the voltage thread while the current thread keep running. And also the thread that retrieves the data from the data server also keep running. I can resume the voltage chart, and at some point there will be the data need to be synchronized. Also, I can pause the current chart just like the voltage chart and then resume it. Finally, the stop button allows me to stop both simultaneously, and if I stop this, everything will stop. So by clicking on stop, all threads, not just the threads for rendering the chart, but also the thread that fetches data from the remote server, the thread that distribute the data from the request channel to the voltage channel and the current channel will also be stopped. So all these threads are child thread of a single parent. So using a single control, I can stop everything without worrying about anything that is left over still running. We measured the runtime overhead of a trivial synchronous and asynchronous computation using async M and promise. As expected, while the overhead for synchronous computation is significant, for asynchronous computation, the relative overhead is not noticeable. Thank you.